All right, in section 1 of our first unit, we're going to be reviewing what it means to be a relation, what it means to be a function, and then what might be new for some of you is what it means to be a one-to-one function. We're also going to look at evaluating functions, which you should have some experience with already. Recall, a relation in mathematics is any correspondence between two sets. Typically, we represent relations with x and y values. You don't have to use x and y, but that's typical. And we say that if x and y are two elements in these sets and a relation exists between the two, then that means x corresponds to y, or y depends on x. Okay? And there's a notation that goes along with this. You have x with an arrow pointing towards y. That's important there, that the arrow points away from x towards y. That's showing that there is a direction. You can't find y without first knowing x. Y is dependent upon x. Okay? Relations can be represented several different ways. You've seen sets of ordered pairs before. You could do a mapping. Notice on the mapping, you just write out your x values first, and from there you draw arrows pointing towards the y value that they correspond to. You could represent them in a table or a graph as well. Okay? Every relation has a domain and a range. Domain is going to be the set of all x coordinates in the relation. Range is going to be the set of all y coordinates. So domain x, range y. And relations would be considered functions if in the relation each element of x, or each domain element, is associated with exactly one element of y, or the range. Okay? Simple way of putting it, to be a function, your x values cannot repeat. Okay? Let's write that down. They cannot pair up with more than one range value. So I have some examples and some non-examples of functions. Over on the left-hand side, you can see the function examples. So the first is a set of ordered pairs. Look at the x values. You have x values of 2, 3, 5, and 8. None of those repeat. Okay? Therefore, we're a function. Second example is a mapping. Notice our input values, or our domain values, are P, Q, and R. See how each one of them has a single arrow coming off of them, pointing towards the outputs. That makes these functions. And then third example is a graph of a function. I can tell that this is a function because it passes the vertical line test. Does not matter where I draw a vertical line on this curve, it's always going to intersect the curve at one point and only one point. If it intersected at more than one point, you would have repeat x values at play. That's not the case here, so we're a function. Non-function examples are over on the right-hand side. Notice in the set of ordered pairs, see how you have 3 repeated, and then you also have 5 repeated. Not a function. On the mapping, see how the input value of Q has 2 arrows coming off of it. It's being mapped to both y and z, therefore not a function. And the circle graphed below doesn't pass the vertical line test. Right? Those 2 points would have the same x value. Okay, what's it mean to be a one-to-one function? Well, it's a function in which each output, each range value, corresponds to exactly one input or domain value. Think of it this way. No y values repeat in order to be a one-to-one function. Okay, so you have relations. Some relations can be functions, and then some functions can be further classified as one-to-one functions. To be one-to-one, your x values can't repeat, your y values can't repeat. There's one x for every one y, and one y for every one x. Over on the left are two examples of one-to-one functions. Notice in the set of ordered pairs, none of the x values repeat, but neither do the y values. Okay? Graphically, in order to check whether something is one-to-one, you want to use the horizontal line test. Okay? The graph on the left, it passes the vertical line test. That makes it a function, but it also passes the horizontal line test, making it a one-to-one function. Notice you're only intersecting the curve at one spot, therefore there are no repeat y values. Over on the right-hand side, two examples of functions that are not one-to-one. Okay? Notice the set of ordered pairs. Your domain values, your x values, none of them repeat. So it is a function, but then see how you have these 2 points with the same y value of 9? That means you're not one-to-one. Look at the graph below it. You have 2 points on this graph that have the same y coordinate. It's not passing the horizontal line test, therefore it is not a function. All right, on this next slide, you are being asked to take the relation that is depicted and determine whether or not it's just a relation, a function, or a one-to-one function. It's asking you to drag each relation underneath its appropriate designation. You can't do that on paper, so what I want you to do is pause the video and take a few moments to just write next to each type of relation what its classification should be. Then you can come back and you can check on the video where I have dragged each relation to. Okay, so take a few minutes to do that. All right, moving forward. So if you know you are working with a function, we have a special notation to go along with it. The notation y equals f of x, I'm sure you've seen it before. It can be used to define a function f, and it's read as y is a function of x, where y is the dependent variable, x is the independent variable. Now, understand, it's typical to use the letters of x and y, but you don't have to. Okay, notice the table here. I have the letters n and q. And we're saying that f of n equals q. So think of n as like your input or domain value, and q is your output or range value. Okay, f of n equals q. What would f of 2 be in this case? Well, the 2 is like an n value. So go to your table, find the point that has an n value of 2. It's right here. And what is its output value or Q value? It would be 6. All right, and then f of what number equals 7? So here we're going in the other direction. The 7 is a Q value. What n value matches up with that? That would be right here when n is 3. Right here we have a function given as an equation. H of p equals p squared plus 2p. We first want to find h of 4. You've done this before, I'm sure. Wherever you see a p, substitute in a 4, and then simplify with order of operations. Oops, let's back up. I didn't put a 4 in right there. So we're saying when you plug 4 in for p, you end up with 24 as your output value. All right? H of p equals 3. So what p value will result in an output of 3? Well, h of p we know is equivalent in general to p squared plus 2p. So substitute that in, set it equal to 3, and what you have now is a quadratic equation. How do we solve that? Move it all to one side and factor. So that's telling me that there are 2 p values that will result in the same output of 3. That means this is not a one-to-one function, okay? Now, take that last example and think about how it relates to the table and the graph here. So we're focusing in on, in the table, these 2 points. We found that when p is -3, h of p would be 3, and when p is 1, h of p would also be 3. And graphically, that would give you those 2 specific points on the curve. All right, last one here, we're asked to evaluate the function h of p with a plus h. So evaluate it with a variable expression, okay? Don't overcomplicate this. Treat it kind of similar to the problem above, where you were just plugging 4 in for the variables. Wherever you see a p, replace it with an a plus h. And then simplify. Careful on a plus h being squared. You got to square the binomial. And then distribute here. Okay. All right, pause the video for a second, try all these on your own, then come back to it and check your work.